In this video, we're going to dive deeper into some of the details of the buffer overflow attack. So we know that we have an attacker over here who is attempting to take advantage of a vulnerable program that has a stir copy or something else that could be overrun using user input, right? And so ideally for the attacker, this vulnerable program would also be a root-owned setuid program. And if they are able to overrun the buffer in a root-owned setuid program and run their own malicious code or injected code, they could launch a root shell. Okay, so we talked about how the attacker is going to have a program that's going to create the payload, and then that payload is going to be read into the vulnerable program and overwrites the stack or smashes the stack, placing the malicious code into the program, into the process, so it can be run, right? So the question that we have right now is, how is the attacker going to produce this payload, right? So how is this payload constructed? In other words, what are the content of this program? So this is a program that creates the payload. How are they going to go ahead and create this payload? Okay, so before we kind of go into a little bit more details about it, right, we need to ask a few questions, right? So we know that the goal is to have this payload overwrite the stack. And we talked about last time how we have very specific things that we need to know. So for example, if we're putting the address of our malicious code, we need to put it in this location of the stack where the return address is, so that the instruction that's run next is going to be our malicious code, right? So we need to know this location exactly before we can launch this attack. So one of the questions we have is, do we know the address of the malicious code after the copy, right? So after the program is read in, do we know the address, right, of this malicious code, right? Because we need to know the address of this malicious code in order to put it inside of here so that it would launch that code, right? It would actually like launch our code and run the shell. The answer to that question is no, we don't know that address. Okay, so let's investigate a little bit further. So another question we might have is, do we know the address of the start of the buffer, right? Because if we know the address of the start of the buffer, maybe we can sort of offset or get that location over there, right? And so do we know the start of the buffer? We actually don't, right? Because when you think about it, right, this program exists. When we run it, the loader launches the program. It's going to assign these memories, these addresses, and we don't know the details. But even though we don't know the details, we can guess, or we can actually make a little bit of an educated guess, right? So the next question is, will we have to guess? The answer for that is sort of. So we're going to have to do some kind of guessing, but we can make a very educated guess, okay? And for this kind of first run through of how we construct the payload, we're going to turn off some countermeasures and assume that we can look up some addresses that maybe we won't be able to if those countermeasures were turned on, right? So for this one, we're going to try and attempt to use exact values for the addresses. Okay, now before we even get into that part of it, I need to give you a little bit of background about Linux, some information about Linux processes, right? And when I'm talking about the Linux processes, I'm talking about this part here, right? So when the program is run, when the loader loads a program into memory, you now have a process running that contains your stack, your heap, environment variables, all of that stuff, right? That's what I'm talking about with the process. So we do know some things about Linux processes. We know that in a 32-bit system, and that's what I'm going to focus on in these videos, but in a 32-bit system, we have 4 gigabytes, which is 2 to the 32, of virtual memory, okay? Now, generally 1 gigabyte is used by the kernel, and so really there's only 3 gigabytes of virtual memory per process. So it's a lot smaller than it looks, right? So one thing that you might think about that we could do if we were attacking the stack or performing a buffer overflow attack is we could try every address. And sure, that is a possibility. Okay, it might be doing something similar in the lab. But anyway, going back to this, so each process has 4 gigabytes of virtual memory, okay? And this isn't the same as physical memory, right? So the physical memory, that's your RAM, right? That's where things are actually stored. The operating system uses virtual memory to manage processes. Now, this is really a topic for operating systems, so I'm not going to go into virtual memory, okay? You can take CS460 for that. But we are going to know that that different processes can have the same virtual address for their stack, okay? And so, so what does that mean? I'm going to just briefly show you this slide. So if I have a program or an executable, and if I load it into memory, so I run it, right? So running it loads it into memory, is executing, then there is process 1. I can also have it running, another version of it running, and that would be process 2, right? And each one of these processes, now look at these processes. If you notice here, I put everything back on here. So we've got starting from the text, data, BSS segments, your heap that grows that way, your stack that grows this way, all of your call stack, and then your environment variables are up top, right? And so we have copies of these, right? So each process has its own virtual memory. And just going back here, most operating systems have the stack start at a fixed address, okay? So what does that mean? I'm just going to put a random number here, but let's say that this stack, I don't know, started, maybe the stack starts growing at location, I'm just going to put a random number in, 400, then this stack would also start at location 400 and they'd grow the same way, okay? And we can look at an example. We can actually turn off address randomization and see that this is indeed true, right? So again, so reminding you, most operating systems place a stack at a fixed starting address, and we can do that because we can disable the address space randomization, okay? So if we know that this is true, then this is the picture that we might have. So physical memory, that's what's located on the disk. And the way that this is working, again, this is just a brief introduction. This is unused. This part here is unused or unassigned memory, okay? And so even though, let's pick something, let's say buffer, right? So even let's say that buffer in both of these cases goes from address, let's go with 200 to 212. I'm just making up numbers, okay? Don't quote these. But if we do have that, then maybe what happens is that this buffer is located, I don't know, I'm just going to put it at this location. And again, the numbers might not match, but you're going to get the idea that in physical memory, right, the address is going to be different. This address here is maybe at location, I'm going to say 3000 or something, and this one's going to be at 5000. Again, different addresses. So they're mapped, right? But the trick here, the main thing to know here is that every time I run this program and load it into memory, every time I do that, if I have address randomization turned off, then this buffer is going to be at the same location. Okay, so I can always refer to it at the location 200 to 212. All right, I think that's really all I want to say about this part. So that's one number one. So one thing is again, I'll go back to it. So stack start at a fixed address. Okay, or in other words, memory addresses are fairly reliable. The other thing to note about that's going to help us with the guessing part is that the call stack is generally shallow. So what does that mean? That means, in general, when we write programs, okay, there are not many, not often, not many deep function calls, okay? The deepest function calls you get are, and you should guess this one, are when we do recursion, right? So whenever we do recursion is when you have a function call in itself, right? Then that's going to create a deeper stack. But those are rare because we know that that slows things down, right? So the general case is that the call stack is shallow. So what does that mean if we're thinking about creating a payload and overloading it over the stack, right? So if I'm creating my payload, I'm trying to draw here, right? So if I'm creating my payload, right, the goal when I'm creating this payload, okay, is that I'm going to start down here, right? And somewhere up top, I've got my malicious code, okay? Knowing that the stack is generally shallow, the call stack is generally shallow, should help me figure out, or should help me determine, like, where the address of the malicious code is going to be, okay? Because the address is, or the call stack is shallow, okay? And we'll see that in just a little bit. So that's the second thing, right? So stacks are at fixed addresses, call stack is shallow. The other background thing I wanted to give you, this is coming from assembly. And assembly, if you remember, is we're talking about machine code level, right? We're talking about moving tiny things from one register to another. All right, we're sort of, so if you think about programming, you have sort of your high level Python, you have your C is the next level, assembly is lower level than that, and then you get to zeros and ones, okay? And so in assembly language, there's this operation, which seems strange. It's called a no-op, okay? It stands for no operation. You can see it written often as NOP, no-op, no-op. No-op like this. I generally will stick with the book format, so it's going to be NOP, and I'm just going to call it a no-op, okay? So a no-op is an instruction, a machine instruction that does nothing. Surprisingly useful, okay, because what it does nothing itself, but what happens is the program counter will move to the next instruction, okay, or the instruction pointer will move on to the next instruction. So as your program is running, your instruction pointer is executing whatever it's pointing to at this point, right? I'm going to try and illustrate this. This is just on the fly, so just bear with me, okay? So if this is my program instructions, okay, and at the low level, the machine level, the CPU level, right? In the CPU, we have these registers. One of them is the instruction pointer, right? Our instruction pointer. Let's do it this way. Okay, so you got your instruction pointer over here. Now, as your program is executing, right, I'm just going to put instruction 1, it's going to execute instruction 1. Maybe that's assigning a variable. Instruction 2 is assigning another variable. Instruction 3, maybe it's doing some kind of calculation. Then it's going to, instruction 4 is going to put the calculation in an answer, right? Now, you can have no-ops as part of your instruction, okay? And then maybe down here, it's a function call, right, which is a jump in assembly, right? So this is a calling a function, okay? And each of these instructions, or each of these instructions has an address, and so the instruction pointer points to the address or the current instruction. So the instruction pointer here will execute in whatever instruction 1, then it will execute instruction 2, then it will execute instruction 3, then it will execute instruction 4. Execute instruction 4, and then it will go ahead and try to execute the next instruction, and you know what that is? It's nothing. It's no operation. It's a no-op, and so it's going to go ahead and go to the next one, right? It just advances the instruction down. And so if you have a program that has a bunch of no-ops in there, then what's going to happen with your instruction pointer, your IP, is it's just going to go all the way until it hits an instruction, okay? And this is going to be very helpful because if you're looking at, I'm going to go back here. Sorry, I'm going to go back here, right? I wanted to get the address of my code exactly. And we're figuring that's a hard thing to do, but we know that there's this gap between the address and where I've put my malicious code. What I can do is I can fill it up with no ops. So now anywhere I can hit anywhere in that space. And what will happen is it will just keep going until it hits a real instruction, which would be over here. Okay. And that's why no ops are helpful. So going back here, oops, wrong one. So going back here, this picture that I did here, the bunch of no ops together, that's called a no ops sled. It's kind of like, I don't know, it's like snakes and ladders. I don't know. You hit the top of the snake and you go sliding down. I guess here you call them chutes and ladders, not snakes and ladders. Anyway, so you'd hit the top of the chute and you go sliding down, and that's a similar thing. In England, it's called snakes and ladders. Sorry for the confusion there. Anyway, that's called the no-op sled. All right. So that's a nice concept. So again, what have we got? We know the address of the stack, number one. We know the call stack is fairly shallow. And then we also know about no-op sled. All right. Just a brief foray into the malicious code. Okay. I'm not going to do that in this video, go into a lot of details in this video. Instead, I'm just going to give you the code to use. Now, the code that we'll use, our malicious code that we're injecting into the vulnerable program, is going to launch a shell, because that would be, that's sort of the ultimate goal of an attacker. And since we're using it on a root-owned setuid program, we're going to be launching a root shell, okay? It doesn't matter as we're constructing the code. All we know is that the code will launch a shell. It's basically bin sh, okay? What does not work is for us to take a C program that launches a shell and then build it, like compile it into an executable and use that. And the reason is because that executable is going to be missing a bunch of things that the loader would do, that would fill things in. So it just doesn't work to take the binary. It's a nice idea, but it doesn't actually work. Instead, we have to write the program directly using assembly, right? And that's what we call the shell code, okay? So what I'll be doing is I'll be giving you the shell code, and the shell code is going to be just a bunch of assembly instructions, all right? Okay. Okay, you might want to pause the video before this one and just have a little bit of a break before we dive into the details now of kind of putting together all that information that I've given you to create our, what's it called, our bad file, right, or our payload, okay? So the goal here, right, the goal of the attacker is to create this payload, right? And so, so in order to do that, we're going to have a few assumptions, all right? We're assuming that we're on the same machine, right? So in other words, that the Linux is launching an attack on the same machine that the program exists on rather than doing it remotely, okay? So that's our first thing. We're assuming there's a bunch of countermeasures turned off, which I'll get into in another video. We're going to use GDB, and GDB is it's like, you know how GCC is our GNU compiler, C compiler? GDB is the debugger, right? It's the GNU debugger. And it's a command line debugger, just like any debugger that we've used in the past, except it's command line. So you don't set the breakpoints by clicking in an IDE. Instead, you're going to just manually do that, okay? And that's what you're going to be doing in the lab. And the reason that we're going to use the debugger is we can what we'll do is we sort of run the program. We'll put a breakpoint inside of our function. So in this, if we're using this example here, my function is foo, then I put a breakpoint inside of there. And then what we can do at that breakpoint is we can get two addresses that are going to be very helpful, okay? One of them is our EBP, or our frame pointer, okay? So we can actually ask the debugger to give us the address of the frame pointer, the register of the frame pointer. So remember from the last video, right? The frame pointer is always located in this location over here. Actually, hang on, I think I've put it in the wrong place. Okay, no, I'm correct. The EBP is right here. So the frame pointer is located right over here, and I can get that address just of a regular running program, right? So I'm going to take my regular program, run GDB, get the address of the frame pointer, right? And this is just running the program normally, running our vulnerable program normally. I'm also going to get the address of the start of the buffer, right? So I'm going to pull this address over here. I'll just name this one start of buffer. The buffer is where we are injecting, right? So when the program is asking for input, right? When the program is doing our stir copy, right? We're stir copying from some location into this destination, right? And so our stir copy is copying from here into starting at this location. So knowing our start of our buffer is going to match this location on the file that we create, right? So with this, we're doing that to get these addresses before we even start constructing our code, right? This is just to get the addresses of the regular running program, or close enough, right? So those are going to be the two addresses that we're going to use. Things to note is that we know that our return address is going to be at location EBP plus 4, right? Because each of these, this is 4 bytes, right? For the previous frame pointer, the address of the previous frame pointer. So we need to know this location over here, and that's at our return address, okay? So we can figure this part out. I'm going to try and draw that. So we know this, right? So we know our return address, all right? What we need to calculate is going to be the offset between the start of the buffer to the return address, right? We need to know this. What is that? We need to know this offset. I'm going to draw that. So this is the offset, right? Let's go all the way to the start of the buffer. Okay, so that's the offset that we need to calculate. So why are we calculating it? We're calculating this offset so that we know when we're constructing our payload that we're going to insert the return address after this offset, right? So we can calculate from location 0 up to that offset, and then we will insert our return address. So we need to know this offset. Does that make sense? So I'm going to call this, I don't know, A, right? I called it A. And so the offset is going to be used to determine the location that we're going to start entering the address of the malicious code. Okay, so that's one thing we're going to have to calculate. Now, how would we calculate that? Well, we can calculate that by going, let's see, so we're going to do the EBP, right, which is this address, we know this, and we subtract the address of the start of the buffer, and that's going to give us this location, and then we add 4. So it's going to be, that's how we're going to calculate it, right? So it's going to be EBP minus start of buffer plus 4, right? Remember, our addresses, our high addresses up here, our low addresses down here, right? So EBP is going to have a higher address than the start of the buffer. So that's the first thing that we're going to have to calculate. Okay, now the second thing that we're going to have to calculate or figure out is B, okay, which is the address of the malicious code, right? Because we want to put the address of our code onto the stack, right? And we have to put it at the correct location, right? So we figured out the correct location using A, but now how do I know what this address or the address of this thing is? Well, remember our no-op sled? We are going to fill our buffer with, fill our payload with no-ops, right? Before we even begin, right? So we fill our addresses with no-ops before we begin. And so then, in order to calculate the address of our malicious code, we're going to go EBP, and we know it's going to have to go above at least 8, right? And we can then put in, we're then going to have to, this is where our guessing comes in. We're then going to have to guess in a few other numbers so that our address can hit anywhere in this no-op sled And the idea of the no-ops is it will keep going, going, going until it hits an instruction that it can execute, and then it will continue and execute our code. Okay, there's a lot going on here, so you probably want to watch this again, this last few minutes again. Okay, so those are the two things that we're going to have to calculate. So when we construct the payload, right? So to construct the payload, this is our program. This is what the attacker is writing this program to construct the payload, right? To construct this bad file. It's going to fill, the program's going to fill everything first with no ops. We're going to place our malicious code at the end, and that's just going to be a copy, some assembly code that we can put in there at the end that launches a shell. And then we're going to place the address of the malicious code at the offset. And to get the offset, we use A calculations, and the address is going to be using our B calculations. Okay? Okay. And so, kind of just to summarize everything, right, is in the lab, what you're going to do is you're going to have this vulnerable program that uses strcpy, right? You're going to use GDB to figure out the frame pointer, the buffer addresses, right? And then you're going to calculate the two values. You're going to calculate the offset. That's going to give us this value here. And then you're going to calculate the address of the malicious code. And what you're going to use these A and B values in this program here that will construct the bad file or the payload. And then you're going to basically try and run the buffer overflow attack on that vulnerable program. So you're going to run the vulnerable program, have it read in your bad file or payload, and what you want to do is end up with a root shell. And it might take a few tries because you might start off by just getting a seg fault, and you just have to keep trying and trying again until you get a root shell. All right, I think that's enough for this video.